A little bit today about detecting climate change impacts on extreme weather. And I gave a seminar in this exact room, I think about 3 years ago, when I was kind of newish here of work that I had been doing. And so this is more of work that I've done over the last 3 years. If you were here and you can remember a slide from 3 years ago, there'll be some commonalities between the two. But what I'm going to try a little bit here is a little bit more of a storyline approach of how I'm not going to go into one specific study and looking at the impacts of climate change on a specific event or a specific type of event. I'm going to walk you through kind of how climate scientists like myself as a whole try to build up understanding of the models that we use to project climate change, and then using that to actually be able to make a little bit more stronger statements in our accuracy of the models that we use about the events that we're interested in. But first, I want to thank, especially in my 4 years here at Stony Brook, I want to thank all of my graduate students. Their work will show up at some point, at least for some of them, in this talk. And so a lot of the especially towards the end of the talk, a lot of the plots that you'll see in here are not plots that I made. It's plots that an analysis that the students have been working on. And in addition, my research is highly collaborative with a lot of the Department of Energy and the National Center for Atmospheric Labs, as well as a lot of my colleagues from other universities. So first thing I want to kind of put this into motivation here is, what are we talking about when we talk about extreme weather? And so most of the time when I'm talking about extreme weather, I'm actually focused from our side of things on the eastern United States, so focused on the United States in general. And here's just a snapshot of what NOAA has defined as extreme weather disasters. These are called billion-dollar weather and climate disasters from 2018. Unfortunately, we didn't have a functioning government for a while, so it's only up to September and not all the way through the end of the year. But you'll see that our extreme weather events in the United States come from a variety of different types of weather events. So particularly of interest is Hurricane Florence, and we're going to see this one come back. So along the eastern coast, hurricanes provide a lot of the extreme weather. You get nor'easters that give us our snowstorms that we get up here. You can have your run-of-the-mill thunderstorms and severe weather. You have your tornadoes. You have hailstorms, which have been particularly damaging in the last year, as well as when you get to the west side of the United States, their extremes typically come from different types of events, oftentimes related to either heat waves and drought, which can lead to wildfires. But they can also get actually pretty extensive flooding from atmospheric rivers. And so this is what we mean by extreme weather. They're extreme, and we're interested in them not just because they're curious and they're rare, but we're interested in them because they have a huge impact on society. Okay, so these are called billion-dollar disasters for a region because they've created over $1 billion, in some cases upwards of $100+ billion in damage due to one event. And so they're extreme in part because they're rare, and they're also extreme because they have a huge impact on society. And so one of the things that NOAA likes to do is they like to plot the trajectory of these extreme events over time. And so what you see here is these are now these billion-dollar disasters starting in 1980 going through September, that's why it's highlighted in red here, of 2018. And the different colors just represent the different type of extreme events. The largest one you kind of see in the end here is green, which is severe storms. And you also see these yellow ones at the top are typically tropical cyclones and hurricanes. And what you can see that there's a very clear trend in the number of billion-dollar disasters we have every year. And the first thing to note is that these are inflation adjusted, so it's just not the fact that $1 billion in 1980 is a different amount today. These are adjusted for inflation, and what you see is there's clearly a trend in the number of disasters that we're having in the United States. And so one of the ideas is that, I'm a climate scientist, so I'm obviously going to, and you can tell by the title, I'm going to try to explain to you that some of this trend is likely due to changes in extremes. But there's also social aspects, right? So there's the impact that now there's more people. The population has increased over the last 30+ years in the United States. The number of people living in urban areas or the number of people living along coastlines has increased significantly in the last 30+ years. So it's not just the changes in extremes that are leading to this trend, but there's other impacts due to society changes and social impacts. But it is clear that if you go to the National Climate Assessment, which comes out every 4 years, we know that changes in extreme weather events are the primary way that most people will experience climate change. And we know for a fact already that human-induced climate change has already increased the number and the strength of some of these events. And so what I'm going to hope to do today is to try to talk about these impacts. And so what is this related to? So this is your kind of climate change 101. Okay, so this is a plot of warming basically of the last 100 plus years in the United States. And so as most of us, as all of us know in this room, we've probably seen a plot like this at some point. And right, so that the temperature is warming on the globe. And this is related in part, right, to increasing global surface temperatures, which are due to increasing carbon dioxide. So I'm not going to go into that. But the idea is that these changes in extremes that the National Climate Assessment is talking about is related to this increase in warming in the climate system, which is due to increases in greenhouse gases. However, what we're really interested in, or at least what our group here is interested in, is that the changes in rainfall. Okay, so I can show you this plot of global average temperature, and that's all well to do. But if you take this to the public and say, oh, it's a degree warmer than it was 100 years ago, let's do something about it, the public's going to be like, who cares? You know, it's going to be warmer. That's great. But it's the impact that comes from weather, which is mostly associated with, so obviously today we're worried about whether it's going to be cold or warm, but typically you're worried about, is it going to rain today or not, right? So precipitation is one of the main ways that society interacts with the weather. And so here's changes now in regional rainfall over that same period. And so you can see in general it's pretty green. That means that we've seen about a 15% increase, particularly in some areas. If you focus on the Northeast, we've seen on cases up to about 10 to 15% increase in mean precipitation in the last 100 years. Okay, so if you go to the public and you say there's been an increase of about 10% of precipitation, again, what can you do with that value? So now if we focus on the extreme precipitation events, so this is now for the whole United States, and let's just say we focus on these 1 in a 5 year events. Okay, so this is your most extreme event that's expected to occur once every 5 years. If you put this is going 1900 to 2010, and it's a 5 year period. If you took this, you can see that the relative number of extreme events in the United States as a whole due to extreme precipitation is increasing. And it's not increasing at this, somewhere between minus 10 and 10%. It's increasing at rates of relative number of events increasing on the order of 40+%. Okay, so now this is a big change in which you could start to really have an impact on society. And furthermore, if you go in and we go to the projections using IPCC class models, you can see that the projections, and this is the Northeast here, are projected to see increases in which you're getting almost double the amount of extreme rain events that you had in present climate. Okay, so it's not just changes in temperature or mean precipitation. What's really changing and having huge impact is a change in extreme precipitation. And these are the events that are causing the majority of damage when it comes to weather. And so the motivation for the rest of the talk is that we are entering an era, these are all the things I'm going to try to show you now in the next half hour or so, is we are entering an era where the numerical tools that we typically use to assess long-term climate change are approaching those that are now used for short-term weather prediction. And so I'm going to show you in a second, but the idea is that the climate and weather fields are starting to really overlap in terms of their numerical tools. And so what this means is that advanced climate modeling has improved our ability to investigate trends in extreme weather, right? So I just showed you a little bit of that on this previous slide here. But they're also being used to project regional impacts of climate change. Because again, providing a global increase of one or somewhere up to 4 degrees globally in temperature on average is not something that you can really act on. And so as a result, these advanced climate modeling techniques are now, there's an extreme increase in the growing possibilities to do what I would call actionable science using climate models. And so for a long time, the climate community has relied on the fact that they create this IPCC report every 5 to 7 years. Sometimes it's getting further and further apart. And that if they create this well-balanced scientific report that proves unequivocally that climate change is happening, that governments will do something about it and that your local officials will do something about it. And what we've learned is that's not how the world works. And so we need other forms of actionable science that can get them to really, that makes it an impact that's local on communities that they can actually understand in a way that can actually help them make change. So what do I mean about the numerical modeling kind of overlapping? And so here's just a plot. I've definitely showed this before. You have, this is scale, horizontal scale, versus temporal scale. So you're going from all the way out to, thousands of meters in scale, so global. So this is very small. Sub-meter, this is global. And this is going from seconds out to decades or centuries. And typically what climate model community has dealt with for a long time has been interested in looking at what creates global variability on the scales of 100 plus kilometers on scales of maybe a month to centuries. Okay, so they're looking at long-term trends in climate change, and they're looking at variability on the order of decades. And so this captures a lot of our at least a lot of our knowing of things like El Nino, seasonal cycles, intraseasonal variability like the MJO, planetary waves like Rossby waves. And so this is all captured in the climate model, and this is what climate modelers typically do. They set up their model, they run for a couple hundred years, sometimes thousands, and they use under different boundary forcings, and they look at projection of climate change. And what the weather community does is, well, they're interested in knowing if it's going to be warming up, if we're going to get out of the 17-degree weather, or if, in the summertime, if that barbecue you've planned for next Tuesday or next Saturday is going to be a great time because it's going to be sunny and 70. So they go out about a week, sometimes a little bit more, and they're working at meters that are on the order of about 10 meters. Okay, or sorry, 10 kilometers. It'd be great if it was 10 meters. 10 kilometer scale. So I actually itched this over, so some models are actually getting a little bit sub 10 kilometer scale in terms of operational forecasts, but still you're focusing on different phenomena. You're focusing on synoptic scale stuff like extratropical cyclones, but particularly tropical cyclones, fronts, squall lines, maybe some of the large-scale features of thunderstorms, but definitely not tornadoes. And so you're focusing on this thing that give us our day-to-day weather, right? Those are where those weather events that we just showed on the billion-dollar disasters come from. And so what advanced kind of climate modeling doing is actually it's pushing this original boundary that was over here. It's pushing it further into the weather regime. And so now we're not operating all the way down to 10 kilometer globally, but we're operating at maybe 20, 25 kilometers globally, which allows us to start to resolve a lot of the synoptic scale features that are important for extreme weather events. And one of the first one that really pops out are cloud clusters, tropical cyclones, and fronts and squall lines. And you'll notice that I actually inched this down, which means we cannot run these things for hundreds of years, like you do a typical climate model. You can run them for a few decades. And so the idea is that this is what I mean, and all the results I'm going to show you for the remainder of the talk come from using a model that can capture a lot of the day-to-day weather variability on decadal timescales. And so we're going to use a numerical model. It's the Community Atmosphere Model version 5. It's created at NCAR in Boulder. It's a climate model, but it's only the atmospheric component. So for all of the simulations I'm going to show you today, we've gridded the Earth into these boxes. And typically, if you have a good climate model, you can capture all these air-sea interactions, ice interactions, land interactions. And what we're doing is we're turning off all the ocean and we're just giving it a temperature, and that's going to determine the flux. So we're using the atmosphere component of a climate model that's conventionally used for climate simulations at 100 kilometers. And we're going to show you some results at 100 kilometers, but also at 25 kilometers. And this is kind of what I refer to as this high resolution or this advanced kind of state-of-the-art climate model that's being used now. And so in this case, all the simulations I show you are atmosphere only, which means they're specified sea surface temperature and land vegetation type. But they are interactive, meaning that the fluxes are calculated, at least on the order of every couple hours. And the same is true for it's a lot more dynamic over land compared to the ocean, though. Okay, and I want to step back and actually I'm going to show you a variety of complexity of simulations. And so most people that aren't climate modelers would just assume that all climate modelers do is just they run these AMIP type simulations. These are the standard simulations. These are the simulations that come out of things like CMIP, which are used in the IPCC. But the idea is that a climate modeler has all these other kind of hierarchical, different complexity types of simulations available to them. We don't have to run with land and continents, okay? We can remove continents and we can look at an aquaplanet, which allows us to understand some of the most fundamental things that drive dynamics in the atmosphere without having to deal with the pesky land and mountains. We can get rid of that, and we can even simplify the boundary conditions even more, which means we can just say, hey, maybe you know what, the SST, the sea surface temperature, is the same everywhere on the globe. Okay, so now you can start to, and so I'm going to definitely show you some of these because these are cool. And then you can start to look at, these are type of complexity that are oftentimes used for individual dynamics of storms or understanding model sensitivities that are typically in the development stage. And so I'm going to show you results from all of these varieties here. To try to get you an idea of how, if you want to understand how extremes are changing, you have to understand how your model works and how your model simulates those extremes so you can actually have faith and confidence in your projections of the extreme events. So first I'm going to talk about changes in extreme precipitation using a very basic approach, using one of these reduced complexity models. So I'm going to take this one. We're going to take an aquaplanet, okay, no continents, no land, prescribed SST, sea surface temperature everywhere. So you have a globe that there is no continents, and the SST everywhere is 29 degrees Celsius. Simple. I've also gone in and changed the insolation so that there is no sun that we're rotating around. There's each data point on the Earth has its own sun that turns off and on throughout the day. Okay, so this is out there, but I'm going to show you how useful this can be for trying to understand those trends in extreme precipitation that we just showed in the motivation. In addition, we turn off rotation, right? That's the simplest form. Let's not have our planet rotating. Let's just try to see how convection behaves basically on its own under warming. And so this is what happens. Okay, so you get these simulations. This is precipitation, and what you see is that it's not moving very much, but in the end you get areas of high precipitation and area of very little precipitation. And it turns out this is a pretty good analogy to what actually happens in the deep tropics, where there is very little Coriolis force. And so the first thing to note is this isn't a novel idea to do experiments like this. Everybody that's a cloud resolving model, so Marat, everybody that does CRM modeling, do these exact same things. They just use small domains, and so doesn't sound as weird as when you turn the whole planet into one of these things. And so what we can do is we can do temperature sensitivity runs. And so this is some work I did with Angie Pendergrass at NCAR. And so what we did is we took this planet here, and instead of just keeping it at this constant temperature, we changed the temperature from 285 Kelvin in 2 Kelvin increments all the way up to 307. Okay, so that's kind of roughing an idea. That's an extreme range of what global warming could be. But we're basically warming this idealized Earth that isn't rotating, that has infinite suns, by 2 degrees, and running these kind of what we call radiative convective equilibrium simulations. And this is plot of precipitation. And what you'll notice right away is that precipitation kind of looks whatever until you get to these really high temperatures. And all of a sudden you get this clumping of convection that produces extreme precipitation. These are rates on average that are over 20 millimeters per day. And actually, if you focus on the extreme rates, they're really high. Okay? So here's our first basic scenario. We said that IPCC projections and National Climate Assessment projections expect that the increase in extreme precipitation in the future. And what we've said, okay, if we take our climate model and we basically operate in the simplest way you can operate a moist atmosphere, we can show you that as you increase warming in this idealized setup, we get an increase in precipitation. Cool. So we know that our simple model is behaving like that. But what we're interested in is extremes. And so first, if you look at mean precipitation, so this is now plotting these global mean precipitation. So as you warm this planet, you'll notice that the precipitation on average, globally average, increases pretty slowly. And if you focus on the mean change in precipitation per degree Kelvin, so just comparing this dot to this dot over the 2 degrees percentage change, you get in general, that's pretty standard. It's somewhere about 4 to 6% increase in precipitation per degree Kelvin warming. And that's expected based upon our near-surface specific humidity, right? So where is this convection getting its energy from? It's getting it from the surface. And so if you increase warming, you increase evaporation, which means you increase moisture in the atmosphere. And so you have a higher humidity near the surface. And so if you look at those dots, they mimic that increase in precipitation quite easily. So you're getting an increase in precipitation, mean precipitation, because you're getting an increase in humidity near the surface. And this solid line here is actually what we expect from the Clausius-Clapeyron relationship. So from theory, we expect an increase of about 6 to 7% per Kelvin in this humidity. And we're kind of following that. We're underestimated a little bit, but we're following that pretty reasonably. So if this was the case, we'd be like, oh, well, we can project the future. We don't even need these fancy climate models to project change in the future. We can do it right now. We have a theory that tells us how mean precipitation changed, so it's over. Well, that's not the case. Because if you look at the 99th percentile precipitation, right, so the precipitation that's the most rare in that domain, and you look at its change in the magnitude of the 99th percentile precipitation, you'll notice that it's kind of standard for some while, around, in this case, around 30 or so, 20 millimeters per day, and all of a sudden at one point it just jumps. And if you focus on the change in that percentage, the magnitude of these dots as a function of temperature, what we see is that it hovers around 0 or a little bit above, so close to 4 in some cases, just like the mean precipitation did, until you get those aggregation situations. And then the extreme precipitation can jump by just changing the temperature, right, by 2 degrees. The extreme precipitation can jump by 80%. Okay, so that suggests that this mean idea of how precipitation changes with climate change is actually wrong when it comes to extremes. That extreme precipitation depends upon the circulations that are developing. And so what this tells us is that first it suggests that while the mean state changes gradually, that extreme rainfall depends largely on organization. What does organization mean in this case? It means it depends upon the weather type. It depends upon the actual event that's providing the extreme precipitation. In this case, it's a clustered storm. And so these are how we use these reduced complexity models to try to understand the basic behavior of precipitation. And now I'm going to jump into a little bit more complexity. But first, I also want to mention that these same type of RCE simulations, these basic idealized crazy planet worlds, are very, very useful. And so here's just an example of some work that we did with the German group and the French group modeling groups, and we basically ran our model all in the same setup, cool temperature, warm temperature, all models get aggregation. The aggregation looks a little different, but we can actually use these models to understand the fundamental change in cloud structure in the future. And so these kind of simple setups have actually been used to try to explore how these anvil cloud, how the deep convective clouds will change in a warming climate. And that's important because those clouds are crucial to global energy balance in the tropics, and therefore globally. And so it isn't just for looking at extreme precipitation, it's looking at some of the most fundamental things that we understand about climate change are actually being come out of these reduced complexity models, even recently. Okay, so let's jump. So that was a crazy planet. Let's jump to some more realistic simulations. So now we're going to run these AMIP simulations. These are basically they're forced with observed SSTs over the historical time period, or using RCP, these IPCC pathways in the future. And we're going to run these models, and we're going to look at climate at differences in tropical cyclones. And so I'm going to go through this pretty quick. This is what a snapshot of that looks like. Okay, so this is 25-kilometer global model, and you can see it looks a lot like there's a lot of detail. And the first thing you notice is tropical cyclones, and those are what we're going to focus on here. And so one of the reasons we can use this model is that if you run a climate model, a conventional climate model that is still used for CMIP5, so for IPCC, or the next IPCC, so CMIP6, that is state-of-the-art, most models run at 1 degree resolution, so 100-kilometer grid spacing. And if you track the number of tropical cyclones in a 1 degree grid spacing for 26 years, this is the number of hurricanes you get. You can count them. Okay, there's a few per year. They take these really weird tracks where they go north and south as opposed to curving like we know. And if the only thing you do is increase resolution to 25-kilometer grid spacing, which pushes you into that weather realm, this is the number of tropical hurricanes you get in that 26-year period. And they start to look a lot more reasonable. They have these paths that come off Africa and go westward until they start to recurve towards the north. And if you compare them to observations, it's pretty good. It's not perfect, but it's like every model has biases, but it's pretty good. So we can use these models potentially. You shouldn't trust. I just showed you this, so you shouldn't trust that we'd be able to use these models for climate change projections of hurricanes, and I'm going to walk you through why that is. But first, the other aspect is that if you look at the same model and you look at extreme precipitation over the United States, okay, so this is a probability density function, right? This is precipitation rate as a function of probability. And so here are your extreme rates. These are your once in every 5-year events that occur. And it's hard to see here, but there's gray shading that represents the observations. And here is your standard kind of CMIP class models. They're these red and green lines. And as we go to high resolution, it turns out in the tail of the distribution, our extreme precipitation events that we were talking about already start to go into that shading of where the observations are. All right, so that's perfect. Great. We're getting extreme precipitation rates that are within the observational range. This model must be better than that model, right? Maybe. But the question is where are these rates coming from? So I just showed you that the extreme precipitation depends upon organization. It depends upon weather types. It depends upon circulation. And so what is contributing to this improvement? Is it because as you go to high resolution, all of a sudden you can get different storm types? So here's an example of observations of Hurricane Irma precipitation from 2 years ago. Is it because these are the events that are giving us an extreme precipitation? So if we've increased our resolution, so now we can get hurricanes where we didn't before, then obviously if we didn't have any hurricanes here, now we have hurricanes, then maybe some of that improvement in the precipitation over land is coming from precipitation associated with tropical cyclones. And so a lot of our work of what we're trying to do is see if the model can capture that. And so here's a run of the model, actually run as a forecast model, not a climate model, and you can see that this same climate model can actually reproduce the extreme rates that are associated with tropical cyclones. So maybe that is part of the improvement. And so that's a lot of what our group is doing. So one of the things that we're doing is we're trying to take these tracks that come out of these climate models. Here's an example track. We're trying to take that track and we say, what does this hurricane look like? So we extract at every time period during this track. And so these lines just represent different 6-hourly, or in this case 3-hourly increments of this hurricane. We can extract the wind field, and we can look at what the wind field looks like. So here's your radius and maximum wind. So you can see at times it weakens to where it becomes really strong, and then it weakens again. Okay? We can see that here in its category in the coloring. And so we can get something here, but we can also use this to define an outer size of the storm, which is shown here by these dots. And that's important because if we want to extract precipitation related with tropical cyclones, we have to know how much to extract, how big is a tropical cyclone dynamically in time. Because you'll notice that the size of this hurricane can change from having a radius of about 500 kilometers to at some point in its lifetime having a radius approaching 1,000. So if you're only extracting precipitation within 500 kilometers all the time, you're missing precipitation that's associated with that storm that's large. And this is something that really has not been done even in forecasting terms of looking at storm size until recently. And so here's what we can do. We can use that. We know where the track is. We can extract precipitation. So here's an example. This is a synthetic storm. This is not any hurricane that's ever existed. This comes from a climate simulation. And you can see that we can now use this method to extract precipitation from tropical cyclones. And what we can do is we can plot all precipitation over the United States. So this is one climate run. This is the number of millimeters per day on average that comes over the lifetime of a 30-year simulation. And we can plot next to it the precipitation that comes from hurricanes only that make landfall or in some cases impact close to land. And so what you can see is, not surprisingly, that most of, on average, on a given year, the number of precipitation from tropical cyclones is pretty small. Because landfall and tropical cyclones in the United States happen a couple times a year. Maybe we can go years without having any. And so when you average that out over over decades, you only get on average, upwards of maybe sometimes, I think these are actually in inches. And so you can, on average, get up to instances where you get 2 inches of precipitation on average in places of North Carolina. But obviously, the year that you have that event, you can get upwards of 30 inches. And so what this suggests is for the first time, we have actually been able to extract TC precipitation, and we can start to compare it to all precipitation. And the interesting thing is that along the coast where you see a lot of maximum precipitation is areas. This is one climate run. You could run the climate over again, and you would get a slightly different distribution in the TC precip. But the idea is it's along areas where you actually have slight increases in mean precipitation. But I already told you, no, we don't want to talk about mean precipitation. We want to talk about extreme precipitation. So that's one of our next steps, and we haven't gotten there. But the idea is we can look at this RX 5-day. So this is your annual maximum 5-day accumulated precipitation. And so here's a plot for satellite observations. And so this means that for any given year, the 5-day accumulated event that gives you your most precipitation that year averages in places along the coast somewhere between 40 and 50. And so it's quite high. And what we can do is we can use this same technique in observations to associate, does that RX 5-day occur when a hurricane occurs? And then you can look at the percentage of the extreme precipitation that's due to hurricanes. Turns out in reality along the coastline, almost 50% of the extreme precipitation at any given year in these areas is due to a hurricane. And so that's the most extreme event. Not on average, right? We just showed you on average precipitation is pretty low. But if you had an extreme event, for example, on Long Island, we have in this case around 25% that extreme event in reality is actually due to a hurricane, that extreme precipitation. And so the next step we want to do, and this actually follows some recent work by Ken Kunkel that's shown the same thing using a different methodology. And so what we're trying to do is build this capability in the climate models. And so we're not quite there yet, but that's something that we're able to do so we can actually validate these models and how well they do against observations. So some other things we do is we run future scenarios. So we look at how hurricanes change in the future. So we can run our same model, and then we can run it in the future. So here is observations, black. Blue is that simulations I just showed you. These are historical simulations of the last 30 plus years or so. And then we can take one of these RCP scenarios out to the future. So this global average temperature out in the future, you're going to see this plot one more time. And so we're going to take this worst case scenario, RCP 8.5. So this is a world basically in which we do very little to mitigate climate change. And we're going to run a 30-year time slice experiment out here and look at the impact on TC frequency. And so one of the things you'll notice right away is the number of total tropical storms, so all tropical cyclones, decreases significantly. First of all, you'll notice we have a slight bias in our model in terms of overall TCs, but you'll notice that it significantly decreases in the future. So a warmer world has less tropical cyclones. What if we focus on just hurricane strength storms that are higher? So these are the ones that do the most damage, right? Again, we see that actually, and this is where our model does actually pretty well at replicating observations, and we see a significant decrease in the future in hurricanes globally. But let's focus on these major hurricanes. These are your category 3, 4, and 5. These are the ones that do the majority of the damage, right? These are the events that cause $100 billion in damage when they make landfall. Here, well, you can see that our model isn't too great at capturing those to begin with, and that's in part because of the limitations of the model. But you'll notice that if you actually do the math, there's over 2.5 times increase in the number of extreme major hurricanes in the future using this model simulation. And so part of the work we're trying to do is well, it's great if I tell you that, but what if the majority of those storms go off to sea and don't ever make landfall? Who cares? And so this is why we're trying to build this tropical cyclone precipitation ability so that we can try to understand if the landfalling storms and the precipitation associated with them are changing in the future. Because that's an actionable science, right? That's something that managers and people that live along these coasts can start to actually plan for. Right now, nobody's been able to tell them that. We just tell them that hurricanes are decreasing on average, but the most intense are becoming more intense. And nobody can do anything with that information. Because if hurricanes make landfall, a major hurricane makes landfall once every decade, or two or few or so a decade, nobody's going to do action on that until they know how certain that is. And so one of the ways we try to get that is we look at distribution. So this is just think about this is instead of showing you individual tracks, I'm showing you a distribution of the tracks, the likelihood of a hurricane happening here on a given year. And what we'll see is we can start to do ensembles. This is novel. Now, for the first time, we're actually able to do ensembles of these high-resolution simulations. And so a key takeaway is that one of these simulations costs on order of about 10 million computer hours. So it takes 10 million iPhones, 1 hour to run, and then you can complete a 30-year simulation. Okay? So if you want it, 5 years ago, we were lucky to have one. So now, architectures of the computers have improved. So we can run 3 ensembles, which the weather community will laugh at this because 3 ensembles is not enough to do much, but it's at least allowing us to give a little bit of understanding of the work that we're doing. And so here's a present climate, here's this future climate, and you can see that this is consistent when you look at an individual basin. The previous numbers were globally. If you look at an individual basin, we again see this reduction, right? So there's less reds, which means the probability of a hurricane happening here in this region is much less in the future than it is now. And so this allows us to maybe start to look at, okay, are regions of landfall changing, right? Maybe they're becoming less common down here and more common in the Northeast. That would be an interesting result. However, we can't really say that yet, because if we take RCP scenario, we don't know what the SSTs are in 2070. We only have climate models that project them for us, and we take those SSTs and we force our model with it. So what happens if we take other projections for RCP 8.5 scenarios from different models, or from a different ensemble of the same model, and look at that? And you can see that the magnitude of that decrease depends very much on the warming pattern in the North Atlantic. So while we can say there's a robust decrease in storms in the North Atlantic using ensembles, the magnitude and the location of where that decrease is maximum is still basically, we can't say anything about it with any certainty. Okay, and so we don't have actionable science to actually do something with these type of simulations yet, except tell water resource managers and folks along the coast that we know that there'll be less. Again, that doesn't really help anyone. We can look at precipitation associated with these storms. Now I've thrown in a medium range, and this is precipitation distribution inside a hurricane. And so just focus on this over here. This means that as the Earth warms from our historical run to our high-res run, we get more extreme precipitation in the hurricane. The probability of having a rate, in this case, of 100 millimeters per day didn't exist in historical climate, and will be something that's actually probable in an RCP, in a warmer future climate. That's what this means. And if we scale that by that Clausius-Clapeyron relationship that I talked about earlier, this theoretical understanding of how much precipitation should change in the future, if we scale that by that, well, that's great. We get all these curves collapse on top of each other. So that suggests the first order that maybe they're scaling as we expect just based upon this theory. And that might be true, but if you still focus on these extremes, this tells you that at this given probability, a storm that would have produced about 80 millimeters per day is now going to be producing 90 millimeters per day. So that's a large increase. And so what this suggests is that, again, that Clausius-Clapeyron scaling does not explain the change in precipitation in extremes. We can do the same thing with these HAPPI scenarios. And real quick, these are just these scenarios of what happens if, instead of the worst-case scenario, this came out of the Paris Accord. If you focus on this kind of this world where we're able to stabilize climate at 1.5 or 2 degrees by the end of the century, how would storms look then? And so we can do the same things. You just focus on global count. We see a decrease in storms. We see a decrease in hurricanes. And we see a slight increase in the most extreme storms. But really what happens when you do these simulations where you have a muted change in the SST is it really complicates things because the aerosol forcing in these models are different. And so that's one of the things that we've looked into. So why are aerosols important for hurricanes? Well, it turns out aerosols like dust can be really important for hurricanes. And so there's been a large literature the last about 10 years ago now that showed in observations that when you have a lot of dust due to emission from the Sahara Desert over the North Atlantic, you have less hurricanes that year. And it's pretty robust. And so a lot of people about 10 plus years ago tried to understand how this might be, tried to use some regional models at the time to try to explore individual storms. But it turns out that this is a very difficult problem to tease out because you need microphysics, you have to have all the direct, indirect effect of aerosols. And so what we've been able to do is to try to explore that using a climate model that can permit tropical cyclones. Because we have the luxury of operating in these weird worlds where we can say, what happens if we take our AMIP simulation? This is now this is showing AOD, so aerosol optical depth for dust. And what happens? Sorry, this is all aerosol optical depth. You can see that there's areas of high dust over the North Atlantic, and we can do this thing where we can play God. We go into our model, we turn off the emission of dust from any dust source. It can no longer emit dust into the atmosphere. We run our model for the same 30-year time period. You see all the large dust-emitting regions of the world have gone away. And we can see that where does this impact over the ocean where hurricanes are? Right here in the North Atlantic. We get this huge decrease in AOD. So there's not dust. There's no longer dust over the North Atlantic and AOD. Why is this important for future climate? Projections using IPCC class models actually suggest that in the future there will be less dust over the North Atlantic. So this isn't just playing God for the sake of it. Where I just mentioned that it's hard to understand these muted signals because these future aerosol forcings are difficult. And what I'm showing you now is that that this is actually something that's projected in the future. And so these type of simulations have two uses. They have us understand our response to that in the model, as well as try to understand what would it be in this world in the future where there is maybe a large reduction in dust. This is not predicting a large reduction, but we're going to the extreme case. It turns out that when you remove dust from the North Atlantic, just focus over here, you see an increase in the number of tropical cyclones per year by 2. Okay, that's like 20% increase in the North Atlantic. That's a large increase. And if you run your model and you try to look at interannual variability in the North Atlantic, so the AMIP model correlates reasonably well with observations, which is black. If you remove dust from the model, the ability to reproduce interannual variability in the North Atlantic goes down drastically. And that suggests it's not only important for for climatology from a standpoint of decreases on average, but it suggests that you can't even get seasons right without the dust in it. And so it suggests that dust is a component, and so this is another thing that makes future projections of climate change really hard. So I want to talk about this real quick. This is an important part, but I'm kind of running out of time. I want to get to one last cool thing. So I've just showed you that the model, we can use these models in advanced formats, and we can try to understand how climate change impacts tropical cyclones. But how do we know? So like now you would step back. Any good reviewer of a paper would say, you haven't shown me yet that these tropical cyclones in this model are even appropriate. How do we know that these are tropical cyclones? What makes them tropical cyclones? Well, we can do some cool things. We can return to the reduced complexity. And so we can have two simulations. So here's our AMIP simulation. This is just showing you tropical wind fields, so you can see every once in a while you get tropical cyclones that spin up. This is a world in which we can remove continents, still have rotation, and we get tropical cyclones everywhere. And so the nice thing about this world is it produces a lot of statistics. This world only has about 90 hurricanes per year. This one has a hurricane forming every couple hours. So statistics-wise, it's great. But we have to notice that the distribution is very unrealistic. But the cool thing we can do with this is we can try to understand the underlying theory. So in a hurricane, there's two things you care about. Oftentimes, there's the intensity, which is often determined by this maximum wind speed at the surface. Turns out that's a very bad thing to use. And the other thing you can look at here is pressure in the center of the storm, right? It's a cyclone. It's a low pressure system. Turns out that if you actually look at this pressure deficit, so how much different is the center pressure from the environmental pressure, that is a great quantity to try to understand theoretically. Because it turns out we have pretty good understanding of gradient wind balance of how hurricanes work. And we can use theory, and we can actually, knowing in this case for this one track, knowing the size of the storm and its intensity and wind speed, we can predict, using theory, the central pressure deficit. We can predict it's a pressure deficit, and then we can compare that. So here's our predicted one, and we can compare that to what the model produces, and it lines up almost perfectly on the line. So what this tells you is that the climate model, even in this crazy idealized setup, is producing the right structure of storms for the right reasons. Okay, this is an example of using that reduced complexity to build up understanding. And so that means is that these models, if you map out that space, that if you look at what the central pressure is dependent upon, it's dependent on wind speed and this size parameter. And the omega, so that idealized world, and the AMIP simulations, the real world, look nearly identical. So they're producing a wide range of storms for the same reasons that's based upon theory. And the nice thing about this is you can compare it to observations, which are very limited. And so it only covers a subset. But again, you can see that it's very clear. And so the advantage here is that we can use this climate model. We're interested in how this one changes in the future, but we can use this idealized world to help us give understanding for how these ones might change in the future, which all can be compared back to observations in the end. So this is just an example of how this reduced complexity can work. And I'm going to finish real quick. I'm going to go 5 more minutes here. With how we can actually try to, now we have a little bit of faith that our model can produce hurricanes for the right reason. And so what we want to do is we want to try to do something more actionable than just providing you with, hurricanes are going to decrease by a couple in the future in the world globally as we know it. Right? That doesn't help anybody. So what we can do is I've already spent, I think, a decent amount of time motivating that these climate models are becoming a lot like weather models. So why don't we just run the climate model like a weather model? We don't have to run it for decades. We could initialize it based upon the conditions outside right now and run a 7-day forecast just like NOAA does for the National Weather Service. So it turns out we're going to do that. Okay, so we're going to use a special setup of the model that only has high resolution over our area of domain that we're interested in, which is the North Atlantic. And we're going to run forecasts in advance of Hurricane Florence. We're going to run an actual forecast. This is your standard initialized on a given day, in this case September 11th at 0Z, and we're just going to run it for 7 days. And then we're going to run a counterfactual forecast. Luckily, we're using a climate model. Luckily, this climate model has been used for climate projections. So we know what the climate model will projects that the increase in SSTs have been for the last 150 years. So we can go into our initial conditions and remove that signal of temperature and humidity from the atmosphere from the initial condition and rerun the forecast. So this is our counterfactual forecast. It's our forecast that would have been without climate change. And so here's what so we run 100 ensembles of each. So we're doing way more ensembles than often some of the operational forecast centers do. But here's the track of Hurricane Florence. Here's when we initialized it way out here. And if you look at the blue or red, which the red is the actual, the blue is counterfactual, you notice that the tracks are very similar. So that's great. That means that this model produces two same storms, even in the world that would have been without climate change. Probability of occurring was 1 because we actually put a hurricane in there, right? We took initial conditions. And they're very close to the track, the observed track over the ocean, and they're very close to each other, which means the model's fit for purpose, which means if we want to understand difference in characteristics that climate change had on this hurricane, we can, the tracks are so similar, we can just look at the difference between the storms themselves, the simulated storms. So that's what we do. Here's observed precipitation from Hurricane Florence. Here's actual forecast from Hurricane Florence. This is an ensemble mean, so the values aren't going to be as high because it's averaged over 100 ensembles. And this is the counterfactual. This is the world without climate change. So eyeballing this right away, you can see that the actual forecast does okay at producing the precipitation, and it definitely has more than the world that would have been without climate change. Okay, so there's an increase in rainfall due to warming. But again, let's look at that from a statistical standpoint. We can plot, in this case, we look at the maximum rainfall rate that occurs within 200 kilometers of landfall. And that turns out for Hurricane Florence was 35 inches, about. Okay, so there's an area in North Carolina that would serve 35 inches of rainfall, which is a lot. We can look at the same thing within 200 kilometers for all the individual ensembles, and we can plot that. That's a red line. It does amazingly good at capturing the maximum rate, right? This is exactly what you want. You have your forecast. Your ensembles are predicting that the maximum cumulative rainfall is very close to what we actually observed. And in the counterfactual ones, you can see that it's shifted to lower rainfall rates. So the maximum rate in the counterfactual world is less. If you look at all rainfall associated with the storm, all rainfall within this 200-kilometer radius, you can again see this pretty large shift. And we're seeing shifts of that the precipitation associated with Hurricane Florence was anywhere from 20 to 30 plus more because of climate change. This is actionable science because this is the science of attribution. This is actually saying, here's two realizations. They do really well at simulating the path of the storm, and we can actually look at the characteristic differences. We can do the same for storm size. We can attribute a large increase in diameter due to climate change. So the storm was larger, which means it impacted more people. And so this is, I kind of threw this in at the end, but this is an example of how we can use all of our understanding. We didn't just go out and do this study and just throw it out there and not having any idea if the model can reproduce hurricanes. We've done, in this case, close to 5, in my case, decade worth of showing that this model is capable of producing storms based upon theory and based upon climate trends. And so this is where we're at now, and we're actually through all of this research, we can actually start to do actionable science that is relevant to stakeholder groups and managers and regions. So final thoughts, a hierarchical approach is crucial to understanding the simulation of streams, and I encourage all graduate students or undergraduates to realize that it's always important to step back, remove complexity to try to understand what you're seeing in your model or in your experiments. As surface temperature warms, we see an increase in mean precipitation, extreme precipitation, but extreme precipitation is increasing at larger rates. And so the thought is that this is coming from things like hurricanes. And so as climate warms, the tropical cyclones are decreasing, but the most intense storms are becoming more intense. And so these decadal ensembles are starting to shed light on regional changes of climate change, but we need more ensembles. That's just the way it is. We're only scratching the surface of what we can do. And that these climate modeling frameworks have been shown now to be robust, and so they can be applied to individual storms for attribution analysis. And this work actually provides additional evidence that climate change impacts on TC isn't just in 2100, it's now. Okay, it's impacting storms now. Weather has changed already because of climate change. And this makes the science much more relatable to the public. And so, some final real quick things. So I focused most of this talk on talking about motivating with mean precipitation and then trying to show you how hurricanes change and how that might impact precipitation. But we're focusing, the group is doing other things. It's looking at severe local storms and how they change with climate. It's looking at extratropical cyclones and how the precipitation associated with them changes with climate, as well as fronts in things like atmospheric rivers. So this is just one piece of the puzzle to try to understand how precipitation changes in the future. So thank you. I went a few minutes over.
Yeah, just question, sort of related, sort of thinking about changes in intensity.
Mm-hmm.
It's something that is really, even forecast models at much higher resolution actually can predict change in intensity of hurricanes very well. So what makes you believe that actually running at 25 kilometers get you correct in the climatological sense?
Yeah, so that's a great question. So it's unfortunately the one part that I've really glossed over. It's one of the parts that gives us the most confidence. And so the model is actually if you focus. So one of the things, the first thing to try to understand of intensity of tropical cyclones is to stop looking at this, one wind speed at some level that you've already interpolated down to get. And so just focus. If you focus on something like central pressure and central pressure deficit, that is something that these models are actually capturing for the exact right reasons. So their storms in general in the model might be a little larger because of resolution, and therefore the wind speed might be reduced a little bit due to gradient wind balance. But they're larger because they're making up for the fact that the model still wants to simulate the right central pressure. And so this gives you confidence that if you look from an intensity standpoint of central pressure, which is a more integrated quantity of intensity because it accounts for things like Coriolis force, size, and stuff like that, that the models do reasonably well. The same would be true, I think, if you looked at a forecast model. In terms of wind speed, that's always a struggle because the observations of wind speed themselves are actually very uncertain. And so comparing just intensity from wind speed is always a risky business. But yeah, this model is absolutely not going to be able to capture. And so when we look at major category storms, those are dependent upon wind speed thresholds, which means they will be impacted by the fact that the model cannot produce the highest wind speeds because it can't resolve the core of the storm, at least a fine storm, as much as it would like. And so that's just one of the limitations. But these type of simulations, especially the attribution type studies, have actually been done with high-resolution regional climate models like WRF, and they can get very similar changes. And so the interesting thing is that the precipitation change signal seems to be, no matter what methodology you're using, is emerging far in advance of any signal in the wind speed intensity or pressure even. So in our forecast of Florence, for example, there is an increase in the pressure deficit, meaning the storm is stronger from a pressure deficit standpoint. But if you look at the wind speed, the uncertainty of them, that they overlap quite a bit because it's a much, much noisier field than something like integrated precipitation. So it's a great point. I mean, it's one of the limitations. It would be great if we could run 1 kilometer global models and forecast models, right? But then there's the people that run the cloud resolving models that are telling you, at 1 kilometer, you're not capturing all these important mesoscale dynamics that are happening in the eye wall that impact intensity, so how can you get intensity right? So at some point, we're never going to be happy with getting these things perfect. We just have to understand, we have to hope that our models are creating the storms for the right reasons, and so that delta change is still useful information. Yeah?
So it seems to me that the public still may not understand this or whatever, but how does the insurance industry, it seems to me the people who are actually going to do something is the insurance industry rather than local managers of the company. Do you interact with them at all? So I don't interact with the insurance industry. So the insurance industry is very much more interested in stuff like this, right? Actionable science. And so the reinsurance industry is actually one of the biggest external funders of hurricane research outside of government, because they are very much interested in it. I don't interact with them much except for at conferences because they have expense checks so they can buy the wine. But so they're interested in it. But water resources managers are interested in certain areas. So we work a lot as part of one of these projects with water resource managers in the Miami region. And they care a lot about, not necessarily these, they're one of the groups that actually care a lot about the future projections. And they have ways in which they've been downstilling CMIP3 data, right? So data from 15 years ago to try to make educated decisions of how to set up their planning for the future. And so there are groups that are interested in it. It's just making sure that oftentimes these stakeholders are using older data, right? So because they're using the data that's been published through the IPCC or something like that, and they don't realize that that's by the time that stuff is published, it's oftentimes 5 years old. And so that's part of the challenges that we have. Yeah, Kamazima?
So let's go back to the reduced complexity.
Yeah.
So you started with the prescribed SST.
Yep.
And I kind of thought you might be getting the right answers for the wrong reasons. Because if you fix the SSD,
Oh, absolutely.
and then you run,
I know where you're going.
and so the patterns you get,
Yeah.
they imply changes which the ocean didn't.
Yeah, absolutely. So we've done the same simulations in which we put a slab ocean. So it's not a full ocean, but we can put a slab ocean. So at least where, if you have a bunch of clouds over somewhere, it's blocking out sunlight, right? So the patch under where the rain is occurring is going to cool, which means it's going to be less favorable to convection. So the convection will break up, but it'll go to the other spot where there's been sun just beating down because all the convection's over here. It starts warming up there, so convection will move. But in that case, there won't be just one blob. There might be a few blobs, but it'll still do the same general stuff. It's just they move around a lot more. But the extreme precipitation just still changes much faster than the mean. So yeah, so we haven't accounted for the fact that in the prescribed sense that you're not allowing for that interaction. But when you do allow for a simple form of the interaction, it still actually has a lot of the same results. It's just a lot more variable, which makes sense. Yeah.
Yeah, I had a similar question to that. I'm really puzzled that you have such a fixed threshold when this one storm system or precipitation event happens. Can you elaborate?
Yeah, so
is that the microphysics or is it the amount of water that it's 302 calories?
So that's an open question. So we have an NSF project that's using a variety of models to try to understand that, because when you look at even these three GCMs, climate models, we haven't focused here, but if you actually look on the individual temperatures, they seem to all do it around the same time. And this is also true in CRMs, which aren't even parameterizing convection. And they also have the same kind of some point where there's like a threshold that switches. And so that's a big part of which we're trying to understand. I mean, the interesting thing about when you have these aggregations, it's actually the least interesting aspect in some regards is these clumps. What's going on outside the clumps is you actually basically what's happening is to allow that clump to form, almost 90% of the globe is actually just emitting radiation out to space to account for it. And so actually how we define aggregation isn't by looking for clumps. We look at outgoing long-wave radiation, because that's one of the indicators that you've aggregated. But why that seems to be a very fixed temperature is actually an active area. It's interesting because it turns out that it's a temperature that's a pretty prominent temperature in the equator region, right? So that the threshold temperature. So it's an interesting aspect from that regard if you kind of look back to what happens near the equator.
Okay, well, thank you very much. This is great. Okay, all right, sorry. You didn't get your hand up high enough for me to say, okay, one more question.
That side of the room was going to be preferable.
Well, he outranks me, so.
So one of the consequences of extreme events when you think about the coastal ocean as opposed to our structures on land is that rivers flush out sediment and they do it in a very nonlinear way relative to precipitation patterns, and recurrence intervals are critical. And so you're altering nutrient delivery and sediment delivery to the coastal ocean. And I'm wondering if anyone is looking at these consequences as opposed to our particular land.
So that's a great question. So the work that's looking at overland precipitation, for example, like this is actually this is just the coastal part of it. There are people that are actually running hydrology models, at least, which is not quite what you're getting at. But so we are looking at the impacts a little bit more than just the rainfall itself. But in terms of you mentioned the reoccurring events, and so that's something that's been a big topic in this area. It's a lot of the water resource managers, particularly in the Susquehanna, which is one of our regions, they're not really interested in like these trends. They want to know what's the likelihood of events happening back to back. And so that's a big area that we're just now starting to get to. Actually, Alyssa and I just talked about that this morning in our meeting. So, yeah.